Welcome to our second lesson on solving difficult trigonometric equations, our second lesson on solving trigonometric equations. These ones are slightly more difficult in that they involve using some of the double angle identities and some other tricks to solve. So our first four problems are just solving some trigonometric equations, and our last one we're going to solve a trig equation but actually use it to think about the intersection of two curves. Okay, let's get started. So let's look at our first problem here. Solve for sine 2x, sine x plus cos x equals 0. So when I look at a question like this, the first thing I notice is that we're talking about a single angle x, but also a double angle sine 2x. So the first, to me, obvious step is to get rid of this 2x using our double angle identity and change it into a 2 sine x cos x. And from that, we kind of reevaluate and see what we've got and how helpful that is. So that simplifies. We have a sine x times sine x gives you a sine squared x. 2 sine squared cos x plus cos x equals 0. And especially when something's set to 0, it's always a good idea to factor. And sure enough, there's a common factor here of cosine x. So we factor that out. We're left with cosine of x times 2 sine squared x plus 1 equals 0. So in order for that to be true, one of those has to be 0. Either cosine of x has to be 0 or 2 sine squared x plus 1 equals 0. Let's start with the easier one. Cosine of x is equal to 0. Well, that happens at pi over 2 or 3 pi over 2. If you're having some difficulty with that still, one thing you could do is you could sketch the graph of the cosine of x, or you could, easier to do is to think about the unit circle. So of course, on a unit circle, if we want to know when cosine is 0, then we're basically saying, when is the x value of the unit circle equal to 0? Well, that's right here, which is pi over 2, but also down here, which is 3 pi over 2, or 90 and 270. And so those are the two answers that we have. Let's take a look at sine squared x equals negative a half. So we started off with, okay, sorry, so this could be equal to 0. 2 sine squared x plus 1 equals 0, which means 2 sine squared x equals negative 1, and sine squared x equals negative a half. Well, there is no solution here. This is not possible. And we can think about why that's not possible. You have to remember what sine squared x means. Sine squared x is really just a shortcut for sine x times sine x, or sine x all squared. So you're basically saying, okay, there's a value of x. When you square it, you get negative 1/2. Well, it's not possible to square anything and get negative 1/2. So that's just not possible. It's like trying to solve something like x squared equals negative 1. There's no real number that works there. And so in this case, we actually just have these two solutions of pi over 2 and 3 pi over 2. Okay, let's look at our second example together. 3 minus 2 cos squared x equals 3 sine x. Okay, so no double angles in this one, but we do have some sines and cosines mixed together, which is sometimes okay. But in this case, with this cos squared x, it's very easy to change that into a sine squared x. So that's probably the first thing you should try. Okay, that's what you get, 1 minus sine squared x. Now I'm just going to expand. I'm going to multiply everything by negative 2 here. So I get 3 minus 2 plus 2 sine squared x equals 3 sine x. Okay, once I've multiplied everything by negative 2, I can take 3 minus 2, obviously, and subtract it. And now I've got this sort of mess here of a sine squared x, a sine x, a 1. I mean, the one thing you need to remember when you're doing this is you kind of it's almost helpful to see this as 1 plus 2x squared equals 3x. Because that's really what I mean, yes, it's a trigonometric equation, but it behaves like a quadratic, in this case a trinomial. And the same, if you see it that way, it helps you realize that probably setting it to 0 is going to be the best thing to do here. And then seeing if you can factor, or if you can't factor, you could actually use the quadratic formula to solve for sine x. We're not going to worry about that right now. I believe this one does factor. So the idea here is to remember that really sine squared x is a lot like x squared, and sine x is a lot like x. And the reason is because x is an unknown value. The sine of x is just another unknown value. It's different than x. I mean, sine x isn't quite the same as having just an unknown variable x. It's different because, for example, we know sine x could never be larger than 1 or less than -1, but in many ways it behaves just like a normal variable. So this is kind of how you can think, okay? And then we have 2 sine squared x minus 3x sine, minus 3 sine x plus 1 equals 0. And then I can think about that as kind of being the same as having like 2x squared minus 3x plus 1 equals 0. If I wanted to solve that equation, I would probably try to factor it, and it would factor. It would factor to 2x minus 1 times x minus 1, or in this case, because we're not talking about x, we're talking about sine x, we get 2 sine x minus 1 times sine x minus 1. If you're not sure why that works, then anytime you're factoring, it's always a really good idea to think about the expansion to make sure you're right. 2 times sine x is 2 sine x squared. 2 times -1 is -2 sine x. But then we multiply by -1 by sine x to get -3 sine x. -1 times -1 gives you +1. Okay, if these two things multiplied together give you 0, then it must be that one of them is equal to 0, either 2 sine x minus 1 equals 0 or sine x minus 1 equals 0. That gives us, if you rearrange this, you add 1 to both sides and divide by 2, you get sine x equals 1/2, and here you just get sine x equals 1. And we have these two answers. Now let's look at this. We'll just go through these in case you're still having a little bit of difficulty understanding why this works. So I'll start with sine x equals 1. To me, that's the easier one. Okay, especially when you have like sine x equals 1 or sine x equals 0 or cosine of x equals 1 or cosine equals 0. I tend to think immediately just about the unit circle. It's not possible to draw a triangle for this one. I mean, sine is y over r, so if those are equal, you can't actually draw a triangle where the hypotenuse is equal to the opposite side. So instead I think about the unit circle, and I say when is each point on the unit circle, its x value gives you the cosine of that angle, its y value gives you the sine. So when is the y value equal to 1? Well, up here, which is of course 90 degrees or pi over 2. For sine x equals 1/2, it's just a little bit different. You got to think about the kind of the cast rule. So remember, that tells us what's positive and where. And we know that sine is positive in these two quadrants because the y value is positive. And so with pi over 6, just my quick sketch right here, we know there's an answer here and there's an answer here. Okay. Sorry, with sine x equals 1/2, we know there's an answer here and an answer over here, where we have 2 is our hypotenuse. Okay, and 1 as our opposite side. Well, of course, this is our triangle 1, 2. This side here would be the square root of 3, though we don't need it in this example. And this angle in here would be pi over 6. Well, the same triangle exists over here because this is still 1 and this is still 2. This is pi over 6, but the angle would be 5 pi over 6, and that's how you get the second answer there. I guess move on to the next example. Okay, here you've got the cosine of 2x plus sine squared x equals 0. And we're going to solve, in this case, for all real numbers as well. Unlike the last two, where I had just the answers between 0 and 2 pi. So, when I look at this, again, I see there's a single angle x here and a double angle. So it's going to be very difficult to solve if we're not, it's almost like having two variables, right? An x and a y in one equation. It's not possible to solve. So it would be nice if we could express it all in terms of x, and we can because we have 3 different double angle identities for cosine. So the question is, which one do we want to use? Well, notice that there's a sine squared x here. One of those identities for cos of 2x gives you an answer just with sine squares, which is probably what we would like. And so that is definitely the first thing I would try. Replace it with 1 minus 2 sine squared x. I'm just going to simplify this next. And I just get, so negative 2 sine squared x plus sine squared x is negative sine squared x. So I get 1 minus sine squared x equals 0. From there, I can say that sine squared x must equal 1, okay? Or negative sine squared x equals -1, and then divide both sides by -1. But either think about bringing that over, but it's definitely what I get. Now, when we take the square root, be careful here. That means that sine x could be plus or minus 1. It's kind of the same idea as when you say that x squared equals -1, that you could have two possible answers, positive or -1. Sorry, you have two possible answers to x squared equals 1, either positive or -1. So here, sine x could be positive or -1. So let's think about when that happens, and we'll explain this answer right here. Just get rid of this for now. Okay, so again, thinking about sine x being plus or minus 1, it's helpful to think about the unit circle. Okay, the y values on the unit circle represent the sine of that angle. So when you rotate to 90 degrees or pi over 2, the y value is 1. So there's an answer at pi over 2. Now the other answer would be down here at 3 pi over 2. Okay, that's where sine x is equal to -1. So these are both answers, pi over 2 and 3 pi over 2. But of course, we're looking for all the possible answers. There are lots. Okay, pi over 2, 3 pi over 2. You could also talk about pi over 2 and then add another 2 pi. So that'd be like 2.5 pi, which is actually 5 pi over 2. Okay, you could talk about 3 pi over 2. You could add 2 pi to that as well, which would be like 3.5 pi, so 7 pi over 2. Those are all possible answers. An easier way to do it, though, is to look at this and say, okay, this is pi over 2. And as soon as I add pi radians, which is like 180 degrees, I get another answer. So all my answers start here, and I can add pi as many times as I want to get another answer. So starting here, okay, this is this KEI part, add pi and you get here, add in 2 pi and you get back to here, add another pi and you get here. You could also subtract pi's because k could be negative. You could start here, subtract a pi, and you'd still be down here. So this is the answer here, x equals pi over 2 plus pi k. Now, there's another way of writing that exact same answer, and that's this right here. So there are a couple ways that you could get this answer. So how some people get this answer right away is they look and they start thinking about listing answers. They notice that the first answer would be pi over 2. The second answer is 3 pi over 2. The third answer would be when you get to pi over 2 again. So that's actually, if you think about 2 plus a half, 2.5 pi or 5 pi over 2. The next answer down here would be 7 pi over 2. That's by the time you've rotated 3.5. And that pattern continues. So those are all the answers. Well, a lot of people in math see these as, like, think of this as being a 1. 1, 3, 5, 7, 9, all the odd numbers. So the way that we can talk about all the odd numbers times pi divided by 2 is to say 2k plus 1 times pi over 2. If k is any integer, then 2k is an even number, and then an even number plus 1 always gives you an odd number. So we're basically saying all the odd numbers times pi divided by 2. So that's what some mathematicians, and I'm including you as a mathematician, that's why some mathematicians, sorry, I didn't mean to show that yet, some mathematicians immediately jump to this way of showing odd numbers. This solution here is fine. I'm okay with this. Another thing I'd like you to notice that if you took pi over 2 and you add pi k, make a common denominator, you'd actually simplify this and get the exact same thing. Now, as much as 2k plus 1 is an odd number, so is 2k minus 1. So this could actually be 2k minus 1. Or if you want, sometimes you see the answer written this way too. This is another way to write the same answer. X equals pi k minus pi over 2. So basically saying, take 1 pi or 2 pi or 3 pi or 4 pi, whatever you want. The pi's always land on one of these two places that I'm pointing out. Like that's 2 pi, that's 1 pi, that's 4 pi, that's 3 pi. So they're saying basically take whatever pi you want and just subtract pi over 2. So maybe I want to do 6 pi. 6 pi puts me here. And then subtract pi over 2. Bam, I'm right there. Okay, maybe I want to do 3 pi. 3 pi, so there's 2 pi plus another pi. 3 pi is right here. Subtract pi over 2. Boom, puts me right there. So there's another way of writing the same answer. So these are 3 solutions, and I'm going to be fine with all 3 of them. I don't care which one you show me. Okay, the last one's probably the most unobvious answer. And then again, there's a fourth one because you could actually change that to a -1 and you'd still be correct. Okay, our last simple solving equation, although this one isn't simple. In fact, this one has a little bit of a trick in it that makes it worth looking at. So sine 2x minus 1 equals cos 2x. And we're just going to solve between 0 and 2 pi. How do we get started here? There's no obvious way to get started. You notice that you have a double angle, but they're both double angles. So sometimes that's not a bad thing. In fact, by the time we're done this question, you might realize if it weren't for the -1, we'd actually be able to solve this without using any double angle identities. Sine 2x equals cos 2x can actually be solved, and I'll show you towards the end. So we're kind of, you look at this, you're almost stuck. So I would think that the first thing we do is, well, let's use a double angle identity. We only have one choice of double angle identities for sine, 2 sine x cos x. Well, once we've broken up the double angle here, I mean, we kind of have to break this one up. We really don't have much of a choice. Now, what to use? Don't have a really good answer. I think I would avoid using cos squared x minus sine squared x. Like I want to have just one of the identities. And when I say one of the identities, I think it's nicer to either just have cosines or sines. So what I chose to do is I chose to use the 2 cos squared x minus 1 as opposed to the identity involving sine and like 1 minus 2 sine squared x. I think you'd be okay with either. And I think if you wanted to try the other identity, you'd find you probably still get the answer. I'm going to stick with this, okay? And when I clean it up, I get this. So the -1s actually, they subtract out. Okay, so they're gone. I have 2 sine x cos x equals 2 cos squared x. Now, I can divide both sides by 2 as well. And I get sine x cos x equals cos squared x. Now, be careful here. A common mistake students want to make is they want to divide out the cosines. Unfortunately, you can't do that when you're solving for x because one solution here is actually cosine of x equals 0. If cosine of x is equal to 0, I mean, this is 0 and this is 0, and the equation is solved. So you're actually dividing by 0 when you do that. I can give you another example of when that's not okay. For example, say you were solving for, let's make it really simple, 4x equals x squared. Okay. You might be tempted to divide both sides of that by 4 and just say that 4 is equal to x. And x equals 4 is a solution to this equation. Okay, the right side would be 16 and the left side would be 16. But there's another solution that works as well, and that's x equals 0. You'd have 0 on the right and 0 on the left. So what do we do instead of that? Well, what we do instead of that is we tend to do something like x squared minus 4x equals 0. And then we factor. And when we factor that, we get the answer of x equals 0 and the answer of x equals 4. So to be very careful when solving an equation to not divide by the value you're looking for. You run into those kind of problems. So instead, I'm going to actually take this and I'm going to apply the same kind of strategy. So that's sort of a common theme in this lesson is treating sine x as if it's a variable like x. And cos x, of course, would be a different variable. So instead I set it to 0, and look, now I've got a common factor of cosine. That makes me pretty happy. Cos x, so I factor out the cos x, and I'm left with sine x minus cos x. Just double check by expanding cos times sine x cos times cos squared. And then the 0 factor theorem, sure enough, there's one of those answers that we knew was going to crop up. Cosine of x could be 0, or sine x minus cos x could be 0. Let's start with the easy one. Cosine of x equaling 0 means that x is pi over 2 or 3 pi over 2. So right away, there are two solutions right there. And we've talked about that before. Keep in mind, we only care about the answers between 0 and 2 pi. Cosine of x is equal to 0. That's already been talked about in this lesson. That's when the x value of the unit circle is equal to 0. Or you could sketch a graph of cosine. Okay, something like this. You could sketch the graph. And as long as you know what the graph looks like, you know that these two x-intercepts, okay, when cosine is 0, happen at pi over 2 and 3 pi over 2. Okay, so that's the easy part. Let's look at this right here now. Sine x minus cos x could be 0. How do I solve that? That's the new, to me, that's the new part of the lesson here. How do we solve something like that? Well, I know that sine x equals cos x, and then there's a number of ways to figure this out. One way to figure it out is to divide both sides of the equation by cosine. So that's actually what I'm doing here, is just dividing the top and bottom by the cosine of x. So that on the right side of the equation, I mean, that's what I did with this right here. So that the right side of the equation gives me 1, and the left side gives me sine x over cos x. And of course, that's helpful because sine divided by cosine is tan. So when is tan of x equal to 1? Well, that happens at pi over 4 or 5 pi over 4. And if you want to just, I'll review that with you very quickly here. Okay, again, think about a triangle. Think about your cast rule. Tan is positive right here. Okay, and if tan is positive right here and tan of x is equal to 1, that means these are both 1, and this actually is root 2, and that's one of our special triangles with a pi over 4 there. But of course, the other possibility is that we're down here, and that our x and, oops, sorry about that, that our x and y values are both equal to -1. There's my pen running away on me there. This would still be root 2 for our hypotenuse, not that we need it. The little related acute angle, or sometimes some people call that the reference angle, is still pi over 4, but the angle that's represented is, of course, pi plus pi over 4, and pi plus pi over 4 gives you that 5 pi over 4. So there are the other two answers. So this particular equation actually has 4 different answers. Now, I would point out that it is possible to solve the equation right here. When is sine x equaling to cosine x? Well, you could reason that out and realize that, look, sine and cosine are equal when we have this special triangle, the isosceles triangle with 1, 1, and root 2. So definitely 45 degrees or pi over 4 is going to be one of the answers, because at pi over 4, both sine and cosine are 1 over root 2. That only happens again down in quadrant 3 when both sine and cosine are -1 over root 2. And so that gives you another answer of 5 pi over 4. It doesn't happen anywhere else. If you think about the unit circle, it doesn't happen anywhere else, okay? Because if you think about being in, for example, quadrant 2, sine and cosine can't be equal because cosine's always negative and sine's always positive. And if you think about quadrant 4, sine and cosine cannot be equal because cosine is positive and sine is negative. And so the only two possibilities are here and here. Anywhere else on the unit circle, it's impossible for x and y to have the same value, okay? If you go beyond, if I go up into here, for example, then my y value is bigger than my x value. Down here, my x value is bigger than my y. And so this is the only place where sine and cosine are equal. So I'm just pointing out, don't worry too much about it. I recommend doing the first method that I've sort of outlined in red, that you take sine x equals cos x, you divide by cos x so you can change it to tan and solve the equation with tan. That'll help you a lot. But it is certainly reasonable that someone like you could look at sine x equals cosine of x, and realize that that can only happen at these values. I just realized that I totally cut off this little triangle here, and I do apologize for that. Let me just, okay, thanks. You don't need my face in the way of this. So this, I was just trying to show you that little triangle again there. So there you are. Okay, let's move on to the last example today. Okay, I'm back. All right, in this question, we're looking for the point of intersection between two graphs. And we'll answer the question algebraically for now, which means we're not going to look at the graphs. We're just going to try to solve without using a graph, just using algebra. And then, of course, at the end, we're going to graph these and take a look and see if that makes sense Okay, so in order to solve this, y equals sine 2x, y equals tan x, I want to know when is sine 2x the same as x? For what x is this equal to true? Is this true? And that will represent a point on the graph where the curves cross or touch. Well, I've got a double angle and a single angle. So by now, hopefully it seems pretty obvious. The first thing I'm going to do is break up the double angle into sine 2x, 2 sine x, pardon me, cos x equals tan x. Next thing I tried is the quotient identity. Take tan x and replace it with sine x over cos x. Notice that some of the strategies that you use in proving trigonometric identities also work very well for solving trigonometric equations, like replacing tan with sine and cosine. I recommend not doing that. If everything were in terms of tan in an equation, then don't replace tan. But when you have sine and cosine and then a tan in there, definitely want to try that. Okay, the next thing I did here was I multiplied both sides of the equation by cosine to eliminate the rational expression on the right. So all I'm doing is taking this, multiplying the left and the right side of the equation by cosine. So the cosines cancel out on the right side. I'm left with a sine, but then of course I have this extra cosine here. I get a cos squared x. And then just like many of the other equations we worked with, set it to 0 with the idea that maybe I can factor. And sure, you can factor out a sine x here. And when you factor this common factor of sine x, you're left with 2 cos squared x minus 1. So one of those has to be 0, either sine x equals 0 or 2 cos squared x minus 1 equals 0. Well, sine x equals 0 is very nice because that's an easy one, 0 or pi. Okay, if you just think about the unit circle and when the y value would be 0 as sine represents, pardon me, the y value on the unit circle for a certain angle. Okay, let's look at the algebra here. 2 cos squared x minus 1 equals 0 means 2 cos squared x must equal 1. Divide by 2, cos squared x must be a half. This is a lot like solving x squared equals a half. And if I wanted to solve x squared equals a half, I would have to take the square root, but I would have to remember that the negative root could count as well. There's a positive and a negative answer. I mean, in this, you'd have both a positive and a negative answer. Okay, well, if you want to do the square root of 1/2, you could think of it as a square root of 1, which is 1, divided by the square root of 2, which is 2. So we get plus or minus 1 over root 2. And that's going to give us a bunch of answers. It's actually going to give us 4 of them. Let me just explain why. So we're looking at the cosine of x, and we want to know when that is positive or negative 1 over root 2. So there's actually going to be 4 possible answers here, 1 in every quadrant. If it was just 1 over root 2, then we'd have 2 answers. Let's look at that. Let's pretend it was just 1 over root 2. Well, that means it's either here, okay, in quadrant 1, or quadrant 2 because of the cast rule. And that would mean that this side is 1. And of course, we have our root 2 here. And basically the same picture over here. The third side of the triangle would be root 3 or negative root 3. And this is a 1. This is like a shared side here, this 1 here. Okay, well that answer is, this is of course that same special triangle, the 45-degree or pi over 4 triangle. So these two pictures here explain how I get pi over 4. They also explain how I get 7 pi over 4. Because one answer is pi over 4, and the other answer is 2 pi minus pi over 4, which is your 7 pi over 4. How about the other two answers of 3/4 pi and 5/4 pi? Well, they're over here because this is 1 root 2, but we also said that negative 1 over root 2 is a possibility as well. And what that would look like is we would have negative 1 here, and then we would have the square root of 2 right here, and the square root of 2 right here. Those are also possible answers, all 4 of these triangles. Okay, I see it as 4 triangles, 1 here, 1 here, 1 here, 1 here. Pi over 4 is their little angle in here. And so this one here is 3 pi over 4 because it's pi subtract pi over 4, which gives you 3 pi over 4. And then the last one here in quadrant 3 is pi radians plus another pi over 4, gives you 5 pi over 4. So you have those 4 different solutions, plus the other 2 right here gives us a total of 6 possible points of intersection. Now, technically, we are looking for points of intersection. So those represent 6 places on the graph where they cross these two curves. I probably want the y value as well, because a point on a graph is usually expressed as both an x and a y value. So what we're going to have to do is we're going to have to take our 6 answers, okay, 0, pi, and these 4 answers, and figure out what the y value is. Now, I can get that y value either by plugging numbers into this equation, y equals tan x, or the first equation, y equals sine 2x. It doesn't matter. They better produce the same y value, because that's the whole point. Hey, look here, they're supposed to be equal. Okay, and if we haven't made a mistake, it should give us the same answer. So I'm going to go through each one of these in order, and I'm going to use, I think I'll use tan x, and I'm going to calculate the y value. So let's do that. Starting with x equals 0. If x equals 0, then y would be equal to, I'll just draw a little here, y equals the tan of 0, which is 0. So 0, 0 is a point of intersection. Okay, the next one, let's look at x equals pi. Gives us y equals tan pi. That is also equal to 0. So pi 0 is another point of intersection. Now that we should understand that. Why do you get 0 here? Why is tan of pi equal to 0? Well, because you know, tan is y over x, and at pi radians you're over here, and your y value is 0, so your tan is equal to 0. Moving on to these guys right here, pi over 4. So at x equals pi over 4, I know I've got y equals the tan of pi over 4. And using those special triangles, that is equal to 1. So we have another point of intersection, which is at pi over 4 comma 1. Okay, next one, x equals 3 pi over 4. X equals 3 pi over 4. We're looking at y is equaling the tan of 3 pi over 4. Okay, which is equal to -1. Okay. Tan of 3 pi over 4 is -1. I'm not going to go through all of these, but that's simply because you're at 3 pi over 4, you're pi over 4 short of pi. And so this is 1, this is -1, and the tan of that is 1 divided by -1, okay, which gives you -1. So there you are. And now you should see the last two as well, which I've just thrown up there for you. If x is 5 pi over 4, y is tan of 5 pi over 4. That is, of course, in quadrant 3. So your y equals 1 for that answer. 7 pi over 4. Okay, you're in quadrant 4 where tan is negative. Okay, this is pi over 4 short of a full rotation, which gives you -1 for your last one. So there's the last two, 5 pi over 4 and 1, 7 pi over 4 and -1. The next thing we'll do here is look at the graph of this solution. So here are the two graphs in Desmos, y equals tan x and y equals sine 2x. I'm just going to change the numbers here aren't very helpful when you're dealing in radians. So if I go to setting, then in the x-axis, I'm going to add a step, which is going to tell me how to label it. I'm going to do pi divided by 4. We'll see what that looks like. And then if you zoom in, you immediately see what it does here. Okay, and we had our points of intersection. Remember, 0, 0 was one of them. You can see that there. There's another one at pi over 4 and 1. Another one at 3 pi over 4 and -1. Pi and 0. 5 pi over 4. Okay, 7 pi. There they were. Those are all the ones that we found. 1, 2, 3, 4, 5, 6 of them. And then, of course, there's lots after that. Now, notice that the y values kind of repeat. So we had the first three, 0, 1, -1, and then 0, 1, -1 again. This shouldn't be shocking that actually when we found the first three, that the next three were the same. The graph of tan, okay, remember tan has a period of pi, okay, it repeats itself every pi radians. And sine 2x also has a period of pi. Sine x has a period of 2 pi, but when you put a 2 in front of it, that horizontally compresses it, so your new period ends up being pi. So both these graphs had the same period, therefore a pi. So it's not a surprise that if that is a point of intersection, this is a point of intersection as well. I think I actually forgot to include that one, didn't I? Because it should technically count. So all the points of intersection occur another pi degrees over. Take 5 pi over 4 and add pi, you get 9 pi over 4. So it's not shocking, for example, that those two are the same. So I'm just pointing out that you can use the period to maybe show a little bit of that. And again, I forgot. I should have included here, technically, x equals 0 pi. I technically should have included 2 pi as a point of intersection as well in order to have answered it correctly. So there's a small mistake I made, not a very significant one. X equals 2 pi, and you would get 2 pi and 0 as a seventh point of intersection. Really the same as 0, 0. But okay, that's it for today.